Okay, good morning and welcome to next lesson in CE3372, lesson 19, which is labeled in our syllabus as hydrology. And currently the link doesn't exist. Let's see why that is. Oh, actually, that's right. It doesn't exist yet. Oh, it's so smart. I named it the wrong thing today. All right. Okay, the index is disabled as it should be for the time being. And so our info will be in PowerPoint in lecture. Let's see if this works now. Spelled correctly. Probably the standard Blackboard doesn't want to ever work. Oh, actually, it's even more insidious than that. It's at the wrong server. That's my bad. So if I could get the interruption, the interferon. There we go. Not perfect, but at least that will get us through today. Copy that. Go here. Put in the correct URL. And then wait. Always wait. All right. Let's try that again. So lesson 19, here's the link. Currently the index is disabled, so it doesn't have the pretty green and black and the clicker doodles yet. And we want to go to PowerPoint, and we're going to want to use this lecture, which is also not PDF'd yet. Open it. And it's not going to get a PDF. You look at that size, 73 megabytes. When you convert a Microsoft product to PDF, you take the number of megabytes the file originally has, multiply by 10, and that's what the resulting PDF document will have. It's because they're all in collusion with the hard drive manufacturer association in the world. Okay, so the lesson for today is we will finish up some of the Goodwin Street example and then leave it, and then we'll go back to it. So Goodwin Street, our goal from last time was to build a network in SWM using the initial design from the rational method that we had in our previous lesson. And then apply a SWM to that. To do that, we're ultimately going to want to invoke SWM as a hydrologic model. So let's go through some of the steps of that, and then we will go back to the example. So the conceptualization for a drainage area is called a subcatchment in SWM. And on the subcatchment, we can choose a runoff generation techniques by choice of an infiltration model. And there's 4 or 5 models built in. Green amped, Horton, modified Horton, curve number, and maybe 1 or 2 others. And then time series of rainfall, the hydrograph is entered in an object called a rain gauge. And so we've seen this picture before. And how we apply SWM as a hydrologic model is each of these 2 drainage areas, the 2.5 acres and the 4.0 acres, are conceptualized as a subcatchment in the SWM computer program. And here's the example just displayed with screen captures. And so the picture was loaded into the SWM program as a backdrop. And then nodes 1, 2, and 3 correspond to particular nodes. And why is it moving on its own? And then at each of the nodes, we supply an invert elevation. So for example, outfall, the bottom node here is set at invert elevation 0. Node 3 in this particular example is at 7 feet. Node 2 is at 9.3 feet. And node 1 is at 14 feet. And the various slopes are given. And so vertical offsets are used at the connections to make all the elevations match up correctly. And this one has 3 2-foot pipes. And here's the important part, the 2 subcatchments. It's all important, but here's the part relevant for today. Here's the 2 subcatchments showed as shaded areas. And for example, subcatchment B-B, which is the 4-acre one, here's where we provide the information about the subcatchment. It connects to node number 2. It takes its data from rain gauge, which is as yet not specified. The drainage area is 4 acres. It's 366 feet wide with a 1% slope, 15% impervious cover. Manning's end of the pervious and impervious is supplied here. Most of the rest of the stuff is set at 0. It's using a type of routing called outlet routing. 100% of whatever runoff is generated gets routed to the outlet, and the infiltration model it's using is green amped. There's no groundwater component, no snowpack, no LID, no land uses associated with it. So that is a fairly minimal subcatchment description. And then we have to choose a runoff generated mechanism. Says for this scale, rational makes sense, but that's not built into SWM, so we need a way to hack it. And the remainder of this describes how you would hack a rational method. And we will exit that and return to this later. I want to go to the actual SWM example because that was enough of the setup. So what we need to do next is we want to return to our Goodwin Street example. And let's see if this takes me to the right place. It's not going to, is it? I want to go to SWM in a box. Okay, cool. It's still there. Let me shrink this. And I've already loaded in the SWM project Hydro 2 Goodwin example. the BIMP, which is readable with a web browser, I think. This BMP. So that'll be loaded into SWM too. And I did that by connecting to the class web server and downloading the BMP file that's in one of the supplementary data things, close tabs. So now let's go ahead and open SWM. So this is a SWM model, that a SWM program that has the base map loaded in. I'm going to unload it, and earlier created a set of conduits. So these are the conduits. They don't have the correct lengths yet, and one drainage area, and then the various nodes. And the nodes don't have the correct invert elevations yet. So basically, this is just the layout. I want to make some modifications on the map display, make things a little bit bigger. Let's make the nodes, yeah, that's big. And let's do the same with the pipes. And I will reload the base map. Okay, so that's pretty similar to where we left off at the end of last lesson, with the exception that I went ahead and built the network outside of class, or outside of your class. And so now our next job will be to use the information that we created when we did the rational method initial design and use it to continue to populate this SWM model. Let me save what I've done right now, okay? And to do that, I need to go to the prior lesson, which was 18, data links. And here's the bitmap I used. Oh, I guess I have to go to the prior lesson even prior, oh, I'm in an infinite loop again. Lesson 17. I want that spreadsheet. So we'll download it and open it. And what I'm after in the spreadsheet is the diameters and the indicated lengths. And then the elevations are going to take a little bit of work on our part to interpret this topographic map. And we'll initially start with just the topographic elevations and then do offsets from that. So I need to have this handy. And I want to start with this. So first thing we're going to get is the pipe lengths. Since I have limited screen real estate, I'm trying to get stuff in something that I can. Okay, that lets me keep enough available. So let's first go and name the nodes correctly. Junction 1,1. This guy is going to be junction 2,1. This one is junction 3,1, 4,1, 5,1, 6,1, 7,1, 5.3, 5.2, 4, 2, 3.2, 3.3, 2.2, 3.1, 1.2. So all the naming is complete, and now we can name the pipes. This guy is pipe. God, I hate the naming convention from this example, 1-1. And its length is 415 feet. Roughness 0.013 would be about right. We'll go change that globally in a second. Our next pipe is 1-2. Its length is 195 feet. I guess I should have the other table where I could get the diameters, but one step at a time. Name, length, roughness, and so on. So we'll go through this for the remainder. This one is pipe 2.1. And its length is 188. 2.2, see 1.2, 2.1. 2.2 to 3.1 is 213 feet. And it is designation 2.2, 2.13. 3.2 to 4.1 is 223. And its name is 3.2. So it's not too difficult to realize this is the hardest part of using SWM, is getting the naming and the drawing done. But we'll have a working example for future use available to us. So this goes from 4.3 to 4.1 or 3.3 to 4? 3.3 to 4.1. So this is pipe number 3-3. And its length is 138. This is pipe, okay, 4.1 to 5.1. This is pipe 4-1. And its length is 193. Or something to 5.1. This is pipe 4.2. Its length is 213. 4-2. This goes from 5.1 to 6.1. That's pipe number 5.1. And its length is 245 feet. A little short pipe here. Pipe 5.2 to 6.1 is pipe 5.2. And its length is 74 feet. 5.3 to 6.1 is pipe 5.3. Its length is 138. Six 1 to 7.1 is pipe 6.1. Its length is 149. Oh, thank heavens, we're done. And pipe number 7.1 to the outfall is 266 feet. And its designation is 7.1. And that's all of that for now. Let's go ahead and get the friction factors correct for everything. So I've drawn a polygon. I'm going to choose Edit, Group Edit. I'm going to edit conduits, and I'm going to change the roughness 0.015, which is on the high side of concrete pipe. Save my work. So then the next step will be to go ahead and put in node elevations. Let's go ahead and do that now. Junction 1.1 is pretty close to 732.3. Let's put the top of all of our pipes 2 feet below the land surface, which is a little bit on the shallow side, but it'll do the job. So 732 minus 2 would be 730. And I'm not going to worry about the 3/10 of a foot. This one's going to be at 723. So 725 to 726 to 721 is 5, so this would be about 2.5, so it'll be 723.5, 23, 22, 21. I'll put this at 721. Okay, so this one will be at 719, and you probably get the point from here. This one will be at half a 7, that'd be 3. Drop 1.5 from 719, 718, 717.5. This is going to be 717. No. 714.7. And the outfall is going to have a pool depth of 715 feet, but the pipe will come in at 7, 15, 14, 13. Okay, I was making numbers up relative to the topographic map. In an actual practice or somewhere USA, you're going to try to do a better job of interpolating than I just did. But that will get us set up for an initial demonstration. So these ones are currently at 0. I'm just going to have to make my best eyeball estimate. 725, 74, 723. Okay, that's good enough for the time being. And let's go ahead and save our work, and we'll generate a profile plot going on the main stem. So we can use the profile plotter. We can select our starting node is that guy. Our ending node is that one. Find path, choose OK, let it generate a plot. And we see that we have a downstream slope. So even though my elevations are pulled out of my datum, they're not bad in terms of slope. There's no low spots and no holes. Holes isn't the right word. Sags. Oh, it's gone into non-response mode. Nice. Network lag. Yep, that's pretty much non-response mode. 32751. There we go, we're back in charge. And so the reason I save my work frequently, more so than I do if it was running on a local computer, whenever I'm running on a remote computer, it seems like they're designed to fail. So looks like it maintained our, let's see if it maintained our, it did maintain our elevations. So we'll save it again. And I want to produce some of the sideways profiles. Let's produce a profile going from here, ending here. And here we see again, everything is sloping downhill like it's supposed to. Produce one more profile just for grins. We'll do this one, start here, end here. So we have one part that's flat. That's not a very good elevation choice I made. So I would be, the drawing suggests to me I need to check something about the relative elevations of junction 2-1 and junction 1-2. Add a couple inches to that, and if we redraw the profile, it's going to look the way we want it to. And now there's a little slope like there's supposed to be. One other thing on profiles, we can have it draw a profile any way we want, although I'm not really sure how it's going to look. So we can pick a junction, and pick a route, add it. This is the one that's going to confuse it. It's a tricky way to pick up the sides and see if the elevations are sloped the correct way. Though I may actually crash the program. We'll know in a second. Link 3. So it actually won't allow us to do that. That's good to know. You have to do them one at a time. That's kind of annoying. One other profile we can look at is this one that picks up these three going across. And indeed, we see that our laterals are draining to the main line. Okay, so we've got the pipes laid out in terms of their lengths. We've got the elevations, pretty good guesses. What we don't have is the pipe diameters entered correctly. We could do that by going back to our diagram down here, and we'll have to manually go ahead and start putting in the diameter. So pipe 1-1 is a 1.25 units, and currently we're in cubic meters per second, which is probably not a very good unit for a problem that's in cubic feet per second. So anyone know what to do to fix that? Sure you do. You go to Project, Defaults, and you change the flow units to cubic meters per second. Press OK. And now it tells us that maximum depth of cross section, those should now be in feet. Let's go ahead and generate an error to at least make it all update. Well, those are now, we know it's in feet now. So next one, we want to put the Pipe 1-2 is 1.5 of those feet. Pipe 2-1 is 1.75 feet. Pipe 2-2, 0.83 feet. Pipe 3-1 is 2 feet. Pipe 3-2, 0.83 feet. Pipe 2-3 doesn't exist. Pipe 3-3, 1 foot. Pipe 4-1, 3 feet. Pipe 4-2, 1 1/4. Pipe 5-1, 3 1/2 feet. This is one over-designed system. Pipe 5-3, 1 1/4. A little teeny pipe. 5-2 is, this one's going to be 3-ish. Pipe 6-1, 3 1/2. And 7-1, 3 1/2. So those diameters, again, were obtained for our preliminary design using the rational method. Save our work. Go ahead, just for fun, we'll do another profile plot. We'll just go around along the main one, and you'll see the effect that we have on changing those pipe sizes. So the profile plot is now reflecting the increasing pipe sizes. And one thing in comment in a sewer system, at the junction, we tend to try to line up the tops of the pipes, and we actually want vertical drops on the downstream side. So this one is nowhere near a final design for either computational or going on to detailed engineering drawing, but it'll be fine for the time being. Okay, so now we've laid out our pipe network. The next thing we could work on is the actual subcatchment. And let me put them up here because I think I can work. Okay, quit moving. Sweet. So this is our subcatchment. For lack of giving it a good name, I'm just going to call it subarea 1-1. So it corresponds to the shaded area that we see here in the drawing. And we use our table to enter what we know about it. We know its drainage area is 2.26 acres. We don't currently know the width, and I'll show a hack for that in a minute. Most of the other stuff we have no knowledge of for the time being, so we'll just leave it as is. And its outlet is 1-1. So it's easy enough to build them and then go back and deal with the intervening data entry as you go. So in part, the computer program is not only a database for storing our work, it also kind of prompts us for information that we need. Let's see if I can get a drawing tool up so I can show what's meant by the width. So I'm just doing this so I can use the drawing tools on the computer, and shapes is what I want. So the SWMM program conceptualizes a subcatchment as that blue rectangle. And the subcatchment can be divided into two parts. Let me go ahead and modify the fill. Okay, so there's our subcatchment, and they all have a common outlet. I'm drawing it intentionally large so I can let's see if I can make that smaller. How do I do that? Deal with this teeny bopper here. And we need a better color for the outlet. Everybody knows that outlets are yellow. No, that's terrible. Okay, so if the outlet's oriented here, this is one type of routing that's performed in SWMM. It's called impervious to pervious, and then so that's one way a watershed, a subcatchment is conceptualized in SWMM. I'll leave that up for a few seconds for the recorder to capture it. Actually, I can do it this way. The second way a watershed is conceptualized in SWMM is like this. See if I can get these to line up correctly. It failed to behave. Well, it is a computer after all. Its purpose in life is to make me want to terminate myself. So this is the second way it will conceptualize flow. And let's check the input. I think there's a third way. And that's all, those conceptualizations are done by the sub-area routing technique. Okay, so impervious, pervious, and then outlet. And go back to my drawing picture. Pervious, impervious, outlet. So this drawing right here is called outlet routing. This is if we choose outlet, because it does that. It takes the pervious portion, computes its runoff, and sends it to the outlet. Takes the impervious portion, computes its runoff, and sends it to the outlet. This drawing gets deleted. This one gets duplicated. The second way it conceptualizes is this one, and this one I believe is called Impervious. I might have these backwards. I think this is called Impervious, no, this is called Pervious Routing. This one's called Impervious Routing. So in that choice we have on sub-area routing, we have the impervious, which is essentially representing this picture, or pervious, which represents this picture, or outlet routing, which represents this picture. Let's go ahead and just capture everything in an outlet, and I don't need its name anymore. So now just a generic area that this represents the whole. It has area, has a slope, and it's going to have something called a width. Oh, I'm going to need those lines. Oh, well, that was stupid. I'll try doing that new spelling, trying to invent new words. So up here is where we enter area, and it has a value in acres if we're using US customary units. Has a value in, I'm pretty sure it's in percent. Yeah, percent slope. The percent slope is the slope of this entire rectangle as it points to the outlet. I don't know how to represent that in a plan view drawing, so I'm not even going to try. But for lack of any better way of doing it, it's a slope along this path, if you will. The width is not necessarily the physical width of the drainage area, because sometimes there is no easy one to do. But it's the hydrologic width of this dimension. And what role it plays is that area divided by equals, where length is the length of, let's make this a blue arrow. So length is in blue. Width will be red. And area, I'm not going to change its color because it'll wipe out if I make it white. So we supply a width. The computer program divides the supplied area by that width to compute a length, and that length is used to compute things like travel times. So that's an important concept. And what that allows the analyst to do is something like this, where the length that matters to them might actually be transverse to the outlet, and then you want to route things that way. So if you read the user manual and documentation manual, a drawing similar to this appears kind of deep in the manual somewhere. But if we want to control time, we control time by length and slope, and we control length by choosing the width. So that was the point of those drawings. So here, for instance, we have this drainage area there. We know the area. We might say that the path length, the longest path is maybe 200 feet. So we would have to take 2.26 acres and figure out what number to divide it by to get a length of 400 feet. So we could take 2.26 acres. We could turn it into feet squared by taking that number and dividing by the number of square feet in an acre, which everyone knows is 43560. So that's square feet. We want a length of 400 feet. So the required width is going to be the square feet divided by the length, 246. So let's just enter 250. That's going to be close enough. So if we make the width 250 feet, we'll have a longest path length of 400 feet. And that will be useful when it's calculating travel times. And then we have to pick an infiltration model. And the infiltration models we have to choose are Horton. The infiltration is in options. Oh, it's gone in non-response mode. Go general. So we have Horton, modified Horton, green amped, modified green amped, and curve number. So if I'm going to approximate the rational method, I usually use Horton. And I approximate it in the following fashion. I double click on it until I get an entry window if it's going to give me one. Yay. What I do is I set my minimum infiltration rate to a pretty high value. Let's say 3. I'll make my max even bigger. So what this guarantees is that if I get 3 inches per hour or greater, it's all going to infiltrate. I don't really worry about these other values. I don't care about the decay constant. I'm picking a minimum infiltration rate that's bigger than my largest anticipated storm flow rate. I'll choose OK. And then I'm going to use the percent impervious as a rational runoff coefficient. And this will generally be a pretty good approximation to the rational method as we've employed it. SWMM was made for a different scale, and by the time it was written, the rational method was considered kind of amateurish. So we put 65%. I'll go ahead and save it. So that will approximate my runoff for that one. Then we work on the next watershed or subcatchment. So we get the subcatchment editor and we do our best to kind of represent its shape, keeping in mind that what we're doing right now is just drawing a picture. So it's not picking up any area information from what we're drawing. And if you're an artist, you can put a lot of effort into the drawing. Trying to get it to close the polygon and it doesn't want, there we go. And so see, this blinking dot is essentially a computed centroid of the polygon. So in this case, the blinking dot's kind of in the wrong place. but again, there's no information confirmed graphically. So I might choose in this case to edit my I want to edit my objects. Basically, I want to regain control of the computer, actually. Let's try that. Okay, subcatchment 17. Vertices. So the problem I have is all these ones here that are smushed close together. Let me just delete the whole thing. Waiting for the command to go over the internet. Okay, you win, computer. I'm not going to wait on you. We'll just, we'll be done with that. So this guy is going to connect to junction 2.1 or 2-1. So we bring in the data entry. First thing is we enter 2-1, hit return. And you'll notice a little itty bitty dashed line just appeared between our subcatchment and our junction. This is drainage area 2-1, so what we call subcatchment 2-1. And because it's requiring San Fernando Valley, we might have to input it again. Yeah. SC. And we would again play the same game to figure out what appropriate distance is. Maybe that one's also roughly that length. See if we can get 400 foot. Yeah, I think that would also be 400 feet. So we have to take its area, which is 3.89 acres. And we'll enter a width of 423 feet. We'll enter a drainage area of 3.89. We'll actually enter the width in the correct cell. Work better that way, 423. Our slope is 0.5%, and our percent impervious, probably somewhere up in the 70. And we'll go to Horton. And then we would repeat that for the remainder. Let's go ahead and put in a rain gauge for the time being, and we'll complete these in a different time because I don't want you to watch me drawing pictures on the computer all day since we're running out of time. So I picked on Puffy the cloud and I clicked on Puffy over here. And now we're going to go ahead and supply Puffy the cloud with some rain gauge information. This is where it gets kind of different than a classical rational method because we're actually providing a hyetograph. So I'm going to create a hyetograph, and if I don't want to use calendar date, we could just do elapsed time in whatever the time interval is. Looks like in this case in hours. So we could go 0, 1, 2, 3, 4, 4, 5, 6. So let's say at the beginning of hour 0, it rains for 0.2. Actually, let's do something that we know. Let's run everything at 1 inch per hour for this first one. So from hour 0 to 1, it's an inch per hour. 1 to 2, it's an inch per hour. 2 to 3, it's an inch per hour. 3 to 4, it's an inch per hour. And then let's say it drops back to 0. Give it some kind of name. And look at a picture of it, and it should look like that, and then it drops back to 0. So that's what we're supplying, and that is as an intensity format. The other format that's in common use is cumulative. Occasionally, we can use volume. I'll let you read those on your own for the time being. I've gone ahead and saved the time series, and now it's saved. Actually, let's give this rain gauge a name other than gauge 1. We're going to call it Puffy the Cloud. So in addition to providing rainfall, Puffy has a very active second job as a DJ in parties on Goodwin Street. So let's go to our subcatchment. Now we'll attach a rain gauge, and it will give us options. We can attach Puffy the Cloud. We can attach Puffy the Cloud to this one. So the way I've done it, all the watersheds receive the same rainfall. If you really wanted to replicate a rational method, you would actually adjust. You'd have a bunch of Puffy the Clouds, a different one for each watershed, or you just do direct input. Let's go ahead and for the sake of argument, let me check the outfall and put it as a free wheelie outfall. So the only way to make this kind of stuff fun is to play games like that. So it's a free outfall. They'll guarantee all the water will get out. So let's go ahead and put a storm on this sucker and see what happens. And make sure I'm set for dynamic wave. Otherwise, I've just wasted an hour of both of our lives. Also very interesting how it keeps changing back into the wrong flow units. Why don't you do what I want you to? Hit save. That's weird. Puffy's all set up. Okay, options. General. We're set up for dynamic wave. I think everything else defaults and it will run. All right, first thing, let's look at the rainfall coming off of our subcatchment. If you recall, the first one had a runoff coefficient of 0.65. So it got an inch an hour, but only 0.65 inches per hour is converted to runoff. So we have 0.65 inches multiplied by our 2.26 acres. So we expect runoff of 2.26 times 0.65. So about 1.5 cubic feet per second should be the biggest runoff that we get. Let's see what happens. Let me try a picture. So this may crash it because it doesn't like to do, oh, it has runoff as our default. So let's go ahead and choose OK. And it produces a peak runoff of somewhere between 1.4 and 1.6. So the runoff rate seems about correct. Currently, we had it start plotting at 15 minutes. So we don't know what happens the first 15 minutes, but we expect the runoff to increase until it hits the peak flow. And so this distance in time represents the equivalent of the inlet time of concentration. So we can jack with the width a little bit and the runoff coefficient to represent proper times of concentration. Let's go ahead and reset one thing on the time steps and rerun it and get more of the curve. See if I can really mess with the program. Okay, that ought to do a good job. And there's what our simulation looks like when we print more of the intervening things. And this shark fin shape is pretty typical for a rational method approximated using a hydraulic model. So subcatchment A seems to be performing as we anticipate. Let's check subcatchment 2.1. Subcatchment 2-1. We'll use the same tool, use the plotting tool. Choose the okie dokie. And it draws that. So 2.1, we're somewhere at 2.6. Let's check the runoff coefficient was 0.7. So that would be 3.89. And our runoff coefficient was 0.7. So we should get about 2.7 CFS, sure enough, about 2.75 here. And if we don't trust the picture, we can also generate a table. Scroll down the table till we get to the equilibrium portion. 2.74, we predicted 2.723. So we're pretty much right on. And getting exact fit between the hydraulic model and the rational method is essentially impossible, but you can get really, really close. All right, let's save our work and return to the actual lecture for today. We actually just went through hacking the rational method, so now we can actually see what we're doing. So to do a rational method, we need an equivalent SWMM model. It has three pieces: a rain gauge, a catchment, and an outlet, as shown here in the picture. At the rain gauge, we put some constant intensity. The example that was used in this setup was 10.9 acres and 1.06 inches per hour right here. And the time of concentration is 49 minutes. Runoff coefficient is 0.32. Applied rain depth is 0.87. And we make some intermediate calculations to get intensity and the required peak discharge by rational method. And so now we're going to apply the initial constant intensity, which is the 1.06 inches per hour, just like we just did in the example. Then in the catchment, we set its size, set it to 100% impervious, and we use that to adjust the width and the slope. So we didn't have to do that. We actually were taking information off of our map to adjust width, and we didn't even adjust slope yet. And this first one gives us an arrival time of 50 minutes and peak discharge of 11 CFS. The peak discharge is intentionally too big, but mostly we're after arrival time. Again, we modify the size and adjust the width and change our arrival time to 50 minutes. And now we'll adjust the catchment information, make the infiltration rates large, set the percent impervious to the actual runoff coefficient, and then rerun it, and we get the correct peak discharge, and we just hacked Q equals CIA into SWMM. Then we can modify the width until we get the the arrival time's correct. And then what we'll do is we'll start to join all those watersheds to one another through the drainage network. Okay, what I didn't do, and this is just an example of a two-area system. You can look at that on your own. Here's another one for a fairly elaborate subdivision drainage system. This is probably overkill for a SWM model, but it illustrates the idea. So there's this small drainage area. I believe you all did something like this for contour maps, this very same watershed. And we want to model the drainage behavior, and each of the little watersheds is shown, and the drainage network is shown. And in this case, the goal was to do it by SCS. So it goes through generating an SCS storm. We've already studied that. We can use HEC-HMS to generate the storm for us because we're lazy human beings. Nothing wrong with laziness if it gets you to the end result faster. And now we can go ahead and drop our SCS into a SWM model, make a couple modifications so that it'll work, and apply it to our fake watershed. And that's pretty much the end of what I have on PowerPoint pre-set up. Let's return to this thing. Good, we left it running. Let's look at our last pipe here. I don't think it provides computer results in the input box. No, it doesn't. But we could model its discharge. So the only place it's getting water from is those two upstream watersheds, which is about 1.5 and 2.75. So 3 points, should about somewhere between 4 and 5 CFS is going to get to this pipe, if any gets to it. Let's see what the computer says gets to it. Somewhere between 4 and 5, and it takes almost an hour for it to get there from the beginning of the storm. Okay, so what was the point of doing that? The point is the profile plots. And like with EPANet, we go to the map and we start marching through time. And we see the water starting to rise up here at the upstream end. Not much water depth in the large diameter pipes. That's not a surprise. We'll let the computer animate for us. And so that's giving us an idea of where the hydraulic grade line is. So let me ask you all a question and we'll call it a day. If the green line in this drawing, so the green line's up here, if that represents the land surface elevation and the blue area represents the hydraulic grade line, and we are indeed only getting input from those two subbasins, is this an adequate storm sewer design? So anybody who wants to can unmute themselves and either answer yes or no. Now, obviously, I'm going to follow up and ask you why you concluded your answer, so be prepared for that. Anybody? Shy people today, huh? Is this an adequate sewer design, yes or no, if the green line represents the land surface elevation?
No.
Why?
Because the sewer is not offset underneath the ground.
Okay, correct. Uh, so let's, hydraulically speaking, because the top of the sewer is exactly at the ground, would it be an adequate design in that case? Okay, I'll answer it. Hydraulically speaking, this is adequate because the water is completely contained in the sewer, which is what we want. Now, the question as to whether these tops are correct or not is something different, because we did make the invert elevations below ground, but that doesn't guarantee that the pipes themselves stay below ground. So the initial elicited answer was actually correct. Hopefully I didn't kill my pro. Good, I didn't. But let's suppose that, for the sake of argument, let's suppose that land surface elevation was somewhere between 732 feet and 722 feet, and the pipe is always underground. Then would you conclude that the sewer is hydraulically adequate? The answer would probably be yes. In fact, you would say the sewer is somewhat over-designed for those particular inputs. But recall, we still have a whole lot of drainage areas not yet reflected, and we'll pick them up next time in the interest of actual time. But that's pretty much the essence of using the SWMM model to test the hydraulics. So if we go to a junction like I'm doing here, and we put the max depth at 2 feet. Actually, let's do that for all of them. Let's suppose that the junction max depth is 2 feet. Now let's actually put this stuff at a decent one. But everything's 6 feet under. That guarantees that the one more profile plot, and I'll re-ask my question. Okay, now let's suppose the green line represents the land surface. Adequate or inadequate sewer design? Anybody? The right side is the outfall, the left side is the upstream. The green line, I arbitrarily declare, is the land surface. Well, I would say it's adequate. The blue line is below the green line everywhere at every time in this simulation. So if this represents our design case, our sewer is at best flowing half full at this upstream end, which is good. Let me stop this guy. There's nothing to be gained now. We're 2 hours into the simulation, so that's pretty much the steady condition. Okay, we will end with that today, and we'll pick up with this by next time. The sewer system in SWM will be completed. So when we go see this, our next class meeting, these other watersheds will have been added. And by then the elevations will be set correctly to reflect where the land surface is and where the invert elevations are. And then we will look at how to represent a dual drainage system where we actually allow overland flow and flow in a sewer system. And that gives you all the tools you need to apply SWM model to most real instances. And as I said earlier, in real ones are far more complicated than this. And the hardest amount of work is data entry, and it can take a while. So let me save my work, exit, press the okie dokie. And we are done with this. Let me log off correctly. Terminate. And did I already close off our, oh, it looks like I already closed off our link to hydrology. Oh, that's right, I don't have a proper index page built yet. So the PowerPoint I presented to you is here in the lecture 19. I'll probably have a link programmed up in a few hours. There are no particular scripts associated with this lesson. There should be no video. These files correspond to a different example. They correspond to the example that said SRC Tanglewild. It's from a different semester. But it's the same type of example as we've just done with Goodwin Street. There's a little PDF that has kind of a how to do rational hack in SWM. And there's the source file for that. And I think that's it for today's lesson. So thank you all very much for your attention. I'm going to stop the sharing and get ready to terminate the phone call. What was the tool used to get? The tool I use is G3 data. If that doesn't work, the drawing an X and Y coordinate with a ruler will work. And let's see if there's a link to that. I think there should be. There we go. G3 data, is there any in the toolkit? Maybe. Go into the old style software. I think it's a 32-bit build. G3 data. And there is a how to use PDF. It's kind of old, but it'll get you through. And so that's what I use to get the XY coordinates. And I believe there's also a video associated with this class that does it. So let's try to figure out when we did that. Would have been either around lesson 2 or 3. So I think this fall 2018 video will have how to use G3 data in it. Yeah, there's nothing in lesson 3. It's lesson 2. I don't think lesson 1 has any video. Yep, lesson 2 is it. So somewhere in here, there should be how to make the contour maps. And then the G3 data is the my preferred tool. The other one you can try is you can try Engage, but that doesn't work super good for me. So I've given up using it. Or you could use real software that you've paid a lot of money for that does the same thing. Yes, Adriana, I guess I should share my screen. That make more sense. I'm clicking away. Okay, in lesson 2, in the video links, either the fall 2018 one will have some discussion of G3 data, or possibly these other ones. And then the source to get a copy is on the content server under software. Go to old style archive, Windows 32-bit, G3 data. It contains a PDF on how to use it from around 2009, so it's sort of dated, but it should be sufficient. The example in the PDF happens to just be a chart, but there's no reason why they can't be XY coordinates on a map. Well, there is no reason. And it also has links. I don't even know if the G3 data site's still, oh, it has links to the GitHub. So you could download it from GitHub and install it. And I think on YouTube, I have a G3 data example. Go to the studio. It's easier to find things. Well, those are pretty old, so maybe I don't have G3 data. Go out to the main YouTube, see what we get from there. Here's other tutorials on how to do G3 data. I thought I had one of my own, but this will get you pretty far along. That's the tool I prefer. So with that, I will stop sharing and does it matter where we put the origin? Technically, no. I would probably locate the origin in the lower left corner where the land elevation's around 70 feet. But as long as you document what you do, it doesn't really matter. And can you just draw it on there, or does it need to be done digitally? You can just draw it on there. All you're after with the contour map, and you've done the contour map before, because you did it earlier in the semester. It's the same. You reuse the same contour map you did for the EPA net model. All you're doing that is to get, when you build your drainage network, you're going to need it for your elevations. That's all you need the contour map for. So with that, I'm going to stop the sharing and end the call because it is now, class is over. Thank you very much for your attention, and I appreciate you joining on a rather, I don't know if it's cold where you all are staying. Hopefully you did not go to campus today and you stayed someplace warm and safe, and I'd suggest you keep doing that because it is pretty cold outside. I opened the door to let my cat out to do his thing in the backyard, which he usually does every morning, and he went out like 2 feet, waited a few seconds, turned around and came back in, and he's like, one of them's curled up behind me, the other one's in bed somewhere. So cats are pretty smart about weather. If they're not going outside, we shouldn't go. So have a great day, everybody. Bye-bye.